proceed.
Okay, so welcome to the third day of BQIT 18. Thanks for showing up early, despite the great time last night. So today we're going to have, I'm going to be chairing your session in the morning. My name is Jorge Barreto. I'm one of the lecturers at the Quantum Engineering Institute at Bristol. And our sessions today is a bit of a mixed match. So essentially we're going to start with detectors work, and then going to continue with a bit of simulations and communications. So first speaker today is Professor Val Zwiller from KTH. He's also a very well-known lead or pioneer in the field of single photon, nanowire single photon detectors, and he's going to be talking about photons alone in the dark, which is very much in my opinion. So thank you very much, and please.
All right, thanks. Shall I turn on my thing now?
Yeah.
Yes.
All right, great.
Well, it's great to be here. Thanks. Indeed, I'll be telling you about photons alone in the dark. The reason being that to really unleash the power of lots of quantum technologies, it's not like I'm in an aquarium or something. Should I keep this sound in this, or? It also sounds like it's about to.
Yeah, volume is too. Should I just talk like that? Yeah, I think it's better and safer, right? So I was saying, to unleash the power of quantum communication, quantum information, quantum sensing, one of the key ingredients is the ability to control light at the single photon level. Right? We want to be able to generate single photon states with high efficiency and high purity and the wavelength we require. And of course, once we generate those and use those for communication, for sensing, we also need to detect them. Otherwise, we'll be wasting our time. So what I'll be telling you about today is these two things: generation and detection of single photon states. I'll touch a little bit on entanglement as well. And indeed, so the work I'll be talking about is mostly carried out at KTH, but we have a spin-off company, Single Quantum, in the Netherlands. We are very close, and we very often, I give you lots of examples, we collaborate. And also, I just wanted to know that both groups are recruiting people, so we're very happy to receive applications. And also, we're also very happy on the side of the company to enter any project you may have where you will need single photon detection. So what's the ideal single photon detector? What are we after? Well, we're after something that will have a detection efficiency of essentially 100%. So we want to be able to detect all and every of the photons that are sent towards our detector. But also we would like to have a very high time resolution. Here I have to come up with a value. I come with 1 picosecond. Okay? But what's interesting about this value, and I'll be talking about this in the coming slides, where's actually the limit? This is a wish list, right? Of course, we don't want any dark on, so we want our detector to only give us detection events whenever a photon impinges, but in no other case. We also want a very short dead time, so this is already pretty short, meaning that we want our detector to be able to detect again very quickly, within a nanosecond. That would be very good, because that would essentially translate into a saturation rate of the order of 1 gigahertz. We'll be able to detect count up to 1 billion photons per second, which for many applications in quantum communication and so on would start to be very decent. And then there's other things to do after pulsing, because when we deal with APDs, especially in-gas type, after pulsing can be a pain. We don't want any polish independence. So this is a wish list. If you have any other elements, I'm very happy to add those and discuss those, of course. Yeah. So how do we ever get there? Are we ever going to get there? This is, of course, just a dream at this point. What happens is over the past decades, is that superconducting nanowires were clearly identified as the way, the paradigm at least, if not the device, to possibly reach these kind of specs. Okay, so that brings me to this new paradigm introduced, that comes from the cold, introduced by Professor Goldsman in Moscow back 15 years ago now. They came up with this fantastic idea. Well, let's use a superconducting nanowire, cool it down below TC, apply a constant current below IC. And lo and behold, when a single photon is absorbed in your nanowire there, what you get at the end of the day is a detection event. Okay? It's essentially, you can see this as a single photon activated fuse. That's what it is. A single photon comes, and the thing goes from superconducting to highly resistive. Okay? For once, nature is kind with us, because we recover superconductivity without doing anything. It becomes superconducting again within pico, or let's say very few nanoseconds. So that's a good thing. So it's pretty easy to use, to implement. What do we have? We have something that works from the UV to the infrared. Okay? We don't even know how deep in the UV, and we also don't know where in the mid-infrared it actually really stops. It gently decays, but can you detect single photons at 10 microns, 15 microns, 25 microns wavelength? The answer is, I think, most likely yes, with a low efficiency, but it remains to be studied. So this is just to tell you that all of these things, also we already have 15 years back of experience, so we don't have all the answers to these very simple questions. Detection efficiency, above 90%. There's a whole bunch of papers out that are already above 90%. So the question is really now, how many nines can we put together? I mean, the next big thing is, we're going to get 99% of efficiency, and then 99.9, right? How many nines can we stack, all right? Time resolution, and I like really to make this clear that this is very crucial. And I'll give you some examples. We really need to also think about time resolution. Too often, I think we're obsessed just with the detection efficiency, whereas the time resolution is essential for many physical experiments. Better than 20 picoseconds is perfectly possible now. And the rest is some things I've already outlined in the previous slide. So this is what we can achieve now. This is what we can really achieve with these type of detectors. Okay? So here is a usual characteristics of the device here. So what you see as we crank up the current we apply on the device up to about 30 microamps, what you can see right here is the detection efficiency going up with the current and then plateauing at some point, right? Reaching something like 92%. This is a telecom wavelength. This is 1.3 microns. Okay. There is a cost to pay. You don't necessarily want to operate right there because in black, what you see in black here are the dark counts. Okay, and the price to pay as you increase the current you apply on the device is that the dark counts are also going to show up and at some point be non-negligible. So you can see that if you were willing to take something like 200 dark counts per second, somewhere there, you will have an efficiency on the order, in this case, let's say 85% or so. But the nice thing is here that this is something you can set during the experiment. From one day to another. You may have some experiment that will require the absolutely highest possible efficiency, and no matter what the dark counts are. And I'll also show you examples later on where what we had to do is get very, very low dark counts, okay? And then be able to sacrifice efficiency and go down to maybe 60% of detection efficiency, but have millihertz of dark counts to be sure that everything you get, all these events you do record are actually photon detection events. So often question, where's the efficiency limit? I mean, 100% sounds like an obvious one, but I mean, there's quite some physics involved, and we need to get our photon absorbed in this piece of metal, right? With 99 or like 100% efficiency. So there are quite some demanding requirements there that we need to address to really reach values very close to 100%. Whereas in cavities and so on, I will go over those things, are obvious things, but still you might scatter out of your cavity mode and so on. So to reach really close to 100%, we will have to be very creative. But nevertheless, these devices, this is now for devices optimized at telecom wavelength, the 1.3 microns gives you the detection efficiency compared to what's also available on the market. Let's say right here, the silicon APDs, and you have the in-gas APDs, so that it's clear that as soon as you're working in telecom frequencies and you want to deal with more or less single photons, the way to go is to use single photon detectors. That's, I think, something we can easily all agree on. Now, time resolution, which I find a lot more interesting, because time resolution, there the limit, the fundamental limit, is not clear, right? No one knows. The best you can come up with, I think, is delta E delta T, right? But we have seen that this goes from the UV to the mid-infrared. So you do a delta E delta T on this, and you end up in the femtosecond range, right? Which anyway, it's one limit, right? So what happened in our case? In the early days, we were using very simple off-the-shelf amplifiers at room temperature, and a typical time jitter, this is a time jitter measurement, right, was on the order of 18 picoseconds, right? This is 3, 4, 5 years back. Yeah. And then what we did, we developed super cryogenic amplifiers that we would place very close in the cryostat, close to our detector, to our super detectors. And what we're able to achieve now is something on the order of 10 picoseconds. This is just by improving the electronics, going from off-the-shelf room temperature thing, a meter away from the detector, to something that is somewhat more involved, operating at 40 Kelvin, very close to the detector, something like 10 centimeters or so. And we're now at 10 picoseconds. This is not the limit. This is absolutely not the limit. I think that we can really set a goal of reaching 1 picosecond. That will take us 5 years or 20 years, I don't know, but that's a goal we can definitely set. Interesting, I'll show you some examples. If you do LIDAR or so, I mean, this is giving you some very high single shot time of travel resolution, yeah? The order of millimeters on the one photon traveling back and forth, you can tell now within millimeters how far it went. And this, of course, also beats largely all of other existing type of detectors. Also, just to tell that it's possible to combine a very high efficiency together with high time resolution. There's no trade-off there. So in this case, for instance, we show a detector that is optimized for 790 nanometers or so. So we reach an efficiency of 80, 85 or so, and at the same time, the very same detector on the same day in the same process gives us a time jitter of about 11 picoseconds, right? And we can do this also for 1550, for instance. This is a 75% efficient detector or so. And then there you combine this with 11 picoseconds of time jitter. So these two things go hand in hand. There's, again, no trade-off. Interesting for one experiment. I mean, this is something that was done in the UK some years ago. This is published back in 2003, together with the group of Buller and Robert Hatfield was here. They used our detectors, so an old version, no cryogenic amplifiers and what have you, very, very primitive type of detectors, but still, doing a LIDAR over a kilometer, okay, eye safe, invisible. This is 1.5 micron lasers, scanned over a kilometer, sent, and the reflection was detected with the telescope over a distance of a kilometer, and this is the kind of images that we're able to achieve already back 5 years ago, right? So you can recognize a human shape, let's say, over a kilometer. And what we have today, if we were to repeat these experiments with what we have today, right? I mean, not only would the image be a lot sharper with the same integration times, but we have reaching resolutions, time resolutions translating into spatial resolutions, which enable you in principle to do facial recognition. Yeah, I don't know if it's good or bad. We're not doing it, but anyway, it's becoming possible. All right. No, time resolution. Another message about time resolution, right? Let's say you're measuring anti-bunching. Many people do that with the detectors. You have your single photon source or entangled photon source, and you want to be sure that you have these single or entangled photons. The measurement you do is this HBT measurement, correlation measurement. And here is a simple simulation where what we do is we assume that our quantum source, quantum dot, quantum single molecule, single atom, ion, what have you, is perfect. It is giving us a beautiful stream of single photons and nothing else. Okay? We give it a lifetime, relative lifetime of 500 picoseconds in our simulation. And now keep this fixed. But now we say the time resolution of our detector is 150 picoseconds. Regular APDs, silicon APDs give you different values. And this is what you get. This curve here that is supposed to go all the way exactly to 0 only goes to 13%. This washing out here, pollution washing out, whatever you want to call it, okay, is due solely to the detector's time resolution that is washing out the ideal peak. Okay. All right. And now let's see what happens when we go from 150 picoseconds to 20 picoseconds. Right. Switching from APDs to SSPDs if you want, and you see that now the pollution is much better. We are now at 2%. So very important. So the take-home message here is, well, detection efficiency is very important, of course, because this is going to set your integration time. But at the end of the day, where you land, the purity of your photon state, right, is going to be given, in many cases, at the end of the day, by the time resolution of your detector. All right. Another thing, I won't have too much time to go in the details there, but this is just as valid. The same thinking is valid also for entanglement measurements. When you do entanglement measurements, you essentially do the measurement I've shown you here, but you do it for all kinds of polarizing bases, HV, VA, DA, you name them, okay? You build this density matrix, okay? And again, if you want to reach a high fidelity, or in this case, a high concurrence, which is essentially the same thing, right? What you require, again, is that your detectors have a very high time resolution, so that the values you put into your matrix are really the values that are given by the process of emission and not, again, polluted by detection. So what we showed here, we did very briefly, we assume again that we have an ideal source of entangled photons, a quantum giving us pairs of entangled photons. And we think, what happens if we use an APD, 150 picoseconds? And you see, the concurrence will peak at not even 0.8. And now we bring in very much faster detectors with 20 or 15 picoseconds of time, and you see that we're able to reach much higher concurrence. So the entanglement, the fidelity, the quality of the entanglement may also be limited in the measurement, right? Very much by the time resolution of the detectors. Which at the time, which is late last year, was surprising to us also. So we also, of course, have to realize the measurement, it seems. Now, what about the single photon sources? One thing we clearly need if you want to implement quantum information type of communication type of things, we need single photons, but at telecom wavelength, because you want to go in optical fibers over tens of kilometers, obviously. And this is not going to work if you're at 900 nanometers or so, so we need to go to 1.3, 1.5 microns. These are nanowire quantum dots, which we're getting from our friends Philip Poole at NRC in Ottawa. And this is a nanowire indium phosphide. There's a little quantum dot right there. And if you take spectra of different quantum, you see that they're able to get us quantum dots that emit sharp lines in the 1.3 micron range. And this is the first, this is the first element, of course, you need. Single photon sources at telecom wavelength, crucial for all kinds of QKD and you name it types of applications. You also need the detectors, and this is an experiment that was done recently, late last year. What they did, this is the group of Rupert Hosing in Vienna. What they did was QKD measurements under the sea. So it's I think the first QKD measurement, they're underwater and international, I think. But this is what we have to put together these days to be innovative, right? So this is done between Malta and Sicily, all right? And using our detectors, which were made at KTH, but all put together, tested, implemented by Single Quantum, they were able to achieve this on the archive for the past week or so. So then we have the detectors. I'm trying to show you, well, the single photon sources are coming up, the detectors are available, they're running, we have them. So to get the ideal, let's say close to the ideal, the required type of single photons that you need for this type of QKD experiments, well, you need to be at 1.5 microns. What I've shown you before was 1.3 microns. So we're applying this growth recipe that was developed by Professor Michler in his group in Stuttgart. We're growing this now in KTH in Stockholm. So we have our quantum dots somewhere there, and we have this DBR below. This is all grown on gallium arsenide, okay? A nice material, easy to grow. And we also put this on a piezo substrate, so we can actually apply a bias on our quantum dots. And this enables us to tune. Okay? So this is what happens. So these are color-coded spectra, photoluminescent spectra, so you said zero bias. On the piezo, you see this is the exciton emission, triune, Y-axis, and what have you, all right? And what we can do now, we can apply a bias on this piezo just below the quantum dots, and we're straining the quantum dots, and the effect of this strain on the semiconductor is just to change the band gap. Okay? So we're changing the emission frequency, this is what you see. So we can tune, we go from 0 to minus 300 volts, we shift it that way, in that direction, you can see, and then we can go to, well, at 0 and then to plus 600 volts, and we can also stop at a given voltage, and this is what we did here. We stop at 400 volts, and we stop for the day. We spend 15 hours there, and we just keep on measuring. And you can see that we are very, very stable. So we can also tune our quantum dots to a very precise frequency and stay there. Keep our piezo tuned to that particular strain, giving us that particular emission frequency. So we have these single photon sources that were tunable at 1.5 microns to be published to come out soon in APL. What we could do, it's not very impressive, maybe it's an old dream anyway, we could then put that light into a fiber, okay, and do spectroscopy on a single quantum dot. So first we can do it the usual way, free space, and what you get is the spectrum shown in black here, okay, there you are, no surprise. But what we can do now is we can put this in a fiber, okay, and measure at the end of the fiber, and we have, in this case, 13 kilometers of optical fiber, and we're still able to do spectroscopy on a single quantum dot over 13 kilometers of fibers, right? Which just happens to be what we could get our hands on in the lab with much longer. Okay. But that's interesting. We have these sources now. Anti-bunching measurements, no surprise here. It works very well in the CW or pulse excitation. So this is just to tell that these are indeed clearly single photon sources at 1.55 microns. Another type of single photons that I'd like to tell you about are very similar, but we're aiming here at 795 nanometers, another wavelength, a magical wavelength, okay? Because 795 is where everything happens in quantum optics, I mean, a lot anyway. This enables us to essentially couple to rubidium. So we're aiming at all these type of hybrid experiments where we have a quantum dot giving us single or entangled photons, and then we couple those with rubidium vapors. I will skip the rubidium part in this talk, with your time. I'll just tell you about how we are able to actually generate single photons and a bit of entangled photons at 795 with this system. So you recognize what I showed you before for telecom. It's the same approach, a piezo right there, DBR, quantum dots, and some whatever optics you can put on top to get the light out. Now we first want to get very pure single photons, step number one. Get them as pure as possible. So what we use is two photon resonant excitation with a biexciton. Okay? So this is the laser we have. So two laser photons that create directly bi-exciton. Okay? And then these three combines, and then it gives us an exciton, and a bi-exciton photon and exciton, and then so we have a cascade of two photons. This is particularly efficient because clean, I should say, because once you get there, you can't, and you get down, you get the emission of the first single photon, this bi-exciton to exciton condition. You are not resonant at all with the laser you have, so you can't re-excite on there. You will be falling back to the ground state before you excite your dot again. So that's just clean, okay? And we can do gravity oscillations. You see those there, so it's telling you that this is already decently clean, all right? And this is again the frequency exactly where we need to couple to the between frequencies. So the schematic of the setup, I already told you about the two photon excitations. So we need to prepare our laser. Here is the sample. We shoot our laser pulse in resonance with the so these two photon absorption process gives us the bi-exciton, and then we send this to our detectors. Okay. Now to show that it's clean, I told you before. I mean, to show that you have a clean source of single photons, you need first of all a clean detector. Okay. So in this experiment, we're going to operate our detectors in such a way that the dark count rate is in the order of millihertz. Okay. And we do so. We reach this by sacrificing a bit of the detection efficiency. Okay. So instead of taking 10 minutes of measurement time, we'll spend 15 to 20 minutes. Okay. But the purity of the measurement is going to be far better. So this is just telling you exactly how this is all implemented. I think I can skip all the details of how this is all built on optical tables. But there's a crash that's involved. Obviously, there's detectors. There's some clever ways to filter the bi-exciton emission from the exciton emission. The detectors are right there. That's essentially the experiment. Of course, I mean, showing half a slide, it took a year to go. And this is the result. But this is the under pulse excitation, and what you see here, each of these pulses here has something like 180,000 correlations, if you integrate all of those. But at time zero here, what we're left with 21 correlations are left, right? And this turns into a G2 of 0 here, which tells you about the purity, right? How purity at 7×10 to the -5. So I think also it's quite something, because it's, as far as we know, the first time that we beat AMO. We have a cleaner source of single photon than ions. Okay, this is a group in Austria. Yeah. And also the best work done so far with quantum dots. So we can generate extremely pure single photon states. And as I said, the dark counts, 10 millihertz on one, 20 millihertz on the other one, means if you do a correlation measurement on the dark counts for 48 hours, nothing whatsoever. So we have no dark correlations. All of these correlations you see are really from photons that are at least flying within the lab, yeah? Very quickly, a few slides about going beyond this and aiming at integrated quantum circuits. So what we can do, these nanowires I've shown you, we can pick and place them. Here is a video that should start. We can pick one with a little tip, okay, and manipulate it. We take it and we go and position it on a silicon wafer. Okay? And what we can do once we have our selected single photon sources placed carefully, but with, let's say, sub-micron precision or so on our wafer, we can build a circuit around those. Okay? So this is what it look like. Here's the nanowire I was telling you about, okay, which we have flat lying here on a silicon wafer. And what we have, then we can just build a waveguide. Silicon nitride is a good material to channel these photons. And this is the real thing. Here's the nanowire, here's the waveguide. You can see anti-bunching at the end of the thing. Then we need to filter and route. This is what we implemented. So we've got this ring resonator. We can warm it up. We have a resistor right there, so we can warm it up. And this enables us to look, we can look then either at the through part or at the drop part, okay? And look at what happens at the through part, for instance. If you look at the through part and you increase the voltage you apply on the resistor, you warm up your ring, okay? So you tune it, okay? What you see, let's look at the T line, the trine from the quantum dot. Well, it comes out, and then it goes out. You don't see it anymore, and then it comes back. When it's not here anymore, well, you can look at the other part, right? The drop part, and look at that. When he's not there, he's there. So we're able to route our single photons from one output to the other. And that's one thing we can do. And we can measure anti-bunching as usual and show that there is still single photons. I mean, nothing happened to the statistics, obviously, after all the filtering. And this is what we look at. Artistic view, this is scalable. The point here is it's scalable. We've done this with 2 nanowires. We've also done this with 6 or 7 nanowires, so there's some scalability to it. You can aim at fairly complex architectures using this. Right? And then we're able to then have a quantum dot here, a quantum dot there, and select whatever comes out. Now, of course, the last thing, this is one of the last slides, what we still need there, we have these single photon sources. They can operate at telecom wavelength. They can give us entangled photons. I didn't have much time to talk about that. We can put those in waveguides. We can couple these waveguides to filters and routers. What we still need to do on that chip, if we want to be complete and throw away our optical tables, is also to do detection, right? We also need to have detectors. And this is work in progress, so I'm showing you very fresh results. So these are not even platinum nitride detectors. They look like this with the SCM. There you go. Which are built on the silicon nitride waveguide. So this was the last element. This is something we are currently studying and testing in our lab. But to be able to also detect single photon efficiently, low noise, you name it, all on the same chip. So outlook, what we have demonstrated that we have nanowire quantum dots giving us bright single photons at any wavelength we desire, essentially. We can couple those into complex structures, waveguides, and so on. We can rug, we can filter, and we're now also introducing high quality, high performance detectors on top of these circuits. So summary, I have shown you that with single photon detectors, we are now at the point where we're able to chase the physical limit. Right? It seems we won't need another paradigm to get really to the quantum limit, to be able to have detection efficiencies approaching unity, to have very high time resolutions, to have essentially no noise. So this enables a very large number of applications. For the quantum dots, we can generate very clean single photon states. Right? We got to a point where AMO is behind, I'll let you say. Let's see what comments I get for that. And the telecom wavelength is also perfectly in range for it. It's also something we can do. And then about quantum circuits, what we have now, we have all the elements, so we have all the ingredients, so we're ready to go and design and realize very complex quantum circuits. All right, thank you for your attention.
Questions?
Hi, thank you very much. I was wondering, when you talk about the entangled photon generation scheme, I may have missed it, but what is the efficiency when you sort of send in a pulse? How often do you get a photon back?
How often do we get a photon back? Very often the detection rate we have on our detectors, so we excite typically at 80 megahertz, regular TISAP laser, and a very typical rate of detection is about 100,000 photons per second on a regular sample, just a dBr below, but nothing fancy at all. And then there is room. I mean, it's being shown. I mean, there's a work in Würzburg together with the group in China, right, where they're getting millions of photons per second. Same scheme, but just nicely engineered light extracting efficiency techniques. So we're in that level amateurs compared to Würzburg and also Paris, right? So 100,000 what you get with a plain vanilla type of device, and you can go for millions.
I was wondering, since you have this spectacular time resolution, can you track the time of arrival distribution of a photon? If you put a photon into some weird traveling mode, wave mode, can you track that?
Sure, yeah. So we like very much not to play with time tagging, right? We know time tag the detection event. That's a very nice way to work. The thing is, we need to find time tagging electronic that actually has 10 picoseconds or so, better than 10 picoseconds of time jitter. So currently, Julien knows the values, but we are able to time tag with that's the best thing on the market, 25 picosecond. If you want to time tag, right? Yeah.
To reconstruct the distribution of the time of arrival. So the limit now is 25.
Well, the electronic, I mean, if you use a fast oscilloscope like we do and then you can do it with the oscilloscope we use has 3 picoseconds of time jitter, right? So that you can use and operate at 10 picoseconds of resolution in your measurement.
So when you move to waveguide devices, often I think these detectors have a much longer absorption
region for your nanowire? Do you have how are you going to integrate the detectors onto the chip, and what kind of timing resolution do you expect when you do that?
We expect, we dream of better time resolution because the wire is shorter. It's really not as long. A typical wire that is built to designed to couple to an optical fiber, we need a length of about 500 microns. And the time jitter, what's left in these 10 picoseconds we have, some of it comes essentially from the length of the wire. Whether you detect, early on the wire or at the very end will give you, because of propagation times, some jitter. So now, once we're on a waveguide, this has been shown by groups in the US at Yale and MIT, right? Once we are able to use much shorter wires, this is going to reduce the time jitter. Okay.
For the nanowire placement, a graduate student still has to do that placement.
Correct, yes.
Have you thought about automation of that, like through some kind of stamping technique, or what you're...
We haven't, I think it's possible. We haven't thought about it because we don't see at this point the need, the use for this approach. I mean, we have done, it takes maybe half an hour to 20 minutes to position one. This means within a day, right, you can make a device that will have dozens of meters. So. But you're right, in the long run, we need that.
I guess we should move on, so thank you very much again.